the graveyard session after lunch. I'll try and keep you awake. This talk is supposed to be a 20-minute talk. I'll probably go through it fairly quickly because it's actually slightly longer than that. There may be some anomalies in some of the pictures and stuff here, but we should do well enough. So I'm going to talk about testing the architecture, okay? But specifically effective architecture for testing, particularly in evolving regulatory environments, which is where most of us will be. So a little bit of background on myself. There'll be a bit of delay when I click, so I'll go through. So I have a technical background, PhD in adaptive framework design. Spent a lot of time C++, standards work, build systems, agile development, speak at conferences on things like distributed teams and so on. And because of the financial crisis, I found myself at the NYSE, and I was there during, obviously, the financial crisis and the flash crash. And some of my systems were involved in this. I was responsible for market data and also for next generation exchange technology. And so I acted as a technical witness to the SEC. So with all of this, I developed a healthy interest, shall we say, for market microstructure. And we spun off our own company called Clearpool. And what we do is we build exchanges, basically. So, okay, so this here is actually, sorry, it's a bit of delay. We'll get around this. So this is actually a very nice sketch, which you can't see because of this is an Internet Explorer, so it's not showing up. But this is a castle. It's an 800-year-old castle. It's from my hometown. And basically, it's an architecture that has evolved. You can't actually see any of the evolution of that because it's just a big black blob. But essentially, it started off being used for defending against attacks with bows and arrows and so on, and over time it now has to deal with artillery and cannons and this sort of thing. And what you would be able to see if you were to look over here would be some widened windows and changes and so on. But anyway, this is our architecture, right? And we want to test it. The trouble is, it's not really easy to do that. In fact, it's very hard. So, I mean, it would be nice if we could, but really we can't. So, what do we mean by architecture, right? This is a key question. So it's the product of the design and the implementation, right? So what we see when we step back and we look at the system. And encoded in this architecture are the choices and compromises that we've made. So these are things like, you know, decisions that marketing made or whatever. So the question is whose choices and whose compromises? I think we're going to have some strange images here. So there are general truths about architecture. It's often an observed sketch of the system. The actual architecture that exists, however, is based on the source code. It's based on the source code and it's based on the deployment and so on and so forth, the manifestation of that. So pinpointing which aspects of the architecture contribute to any characteristic of the system can be very difficult. And this is obviously one reason why it's hard to change, and it's also why it's hard to test. We also have environmental influences which impact our architectures. Some of them are shown here, but typically team composition, the teams that form to build systems, organizational structure. If anyone's heard of Conway's law, then this is it. The regulatory environment, a big one for us, and performance and constraints. And what we see with things like MiFID II is that we actually have performance constraints encoded into the regulations. So we're getting to a stage where this can all be quite difficult. And these are moving targets. And because of that, it's very hard to figure out where we are. Not only that, but regulations, for example, are triggered and skewed by events. This is why the flash crash brought in a lot of regulations. We have an interest in high-frequency trading, rightly or wrongly. And a lot of these things have influenced heavily both the environment and then obviously the systems we build. So we've also seen an explosive growth in this regulatory burden. And if we look across the pond to the US, it's a good example. What we see down here in the bottom are 3 of the primary banking acts for the US. So the National Banking Act 1864, 29 pages that said this is how the banking system should work. In 1917, this was updated, 32 pages, the Federal Reserve Act. We then had the biggest financial crisis of our time, which was the Wall Street crash, 1929, which brought in the 10-year the Great Depression, and the markets didn't recover for 50 years after that date. So, I mean, that's pretty phenomenal. In response to that, we had the Banking Act in 1933. So we had a bit of a bake time, thought about it, produced this, 37 pages. also referred to as Glass-Steagall Act, by the way, for those that aren't familiar with it. In response to the 2008 financial crisis, we have Dodd-Frank. Dodd-Frank weighs in at an impressive 848 pages. Now, these 848 pages are not actually rules. They are a framework for the rules that need to then be written by the legislators. And in fact, at the last count, by some measures, about a third of the way through is about 15,000 pages. Now, you can imagine the number of billable hours that the legal teams would have as a result of this. Quite impressive. So this is the environment that we're in. These are the things that influence our architectures. Okay, so if we simplify this, we can see that we have basically business rules, performance requirements, regulations. We interpret these, and we end up with the architecture or the technology that we need to satisfy these issues. So we have a lot of problems, and whenever the clicker clicks, oh, there we go. So we have a lot of problems, and they all influence our systems. They also influence each other, and of course, you know, I'm listing random ones here, but I mean, we're just scratching the surface. Any reasonable system that we will build will have a lot more going on than this. So in order to understand this, we need to understand problems. So Russell Lakoff was an organizational theorist and systems thinker, and in 1974 he said, we solve the wrong problem, we fail more often because we solve the wrong problem than because we get the wrong solution to the right problem. So what we want to do is understand how do we classify problems and what can we learn from that. And it turns out there's a great deal of research in this. It goes back about 50 years. And we can basically characterize problems in three different ways. We can characterize them as tame. Now, tame problems are not simple problems. They could be very, very complex problems, but what they do have is a definitive stopping point. And you can break these problems down into parts and deal with them piecemeal. And when you're done, you actually know, are you successful or not? Have you been successful? So you can take a nice linear approach to solving them, and this is good. Now, there's another class of problem, another way we can characterize problems, and what you can't see here is a data center with the backs of racks with lots of network cables hanging out. Instead, you can see a black blob. But trust me, there was a big mess here. So this is the other kind of problem. Now, these are proper terms. And this is about organized complexity. So it's clusters of interdependent and interrelated problems, problems which cannot be solved in relative isolation to one another. And this is a key point. So they're more like puzzles. So the thing about messes is that because we can't just break the system into parts to understand it, we need to look for patterns, right? So we see this in software. We have software patterns. It's a similar idea. But we also have to be careful if we misidentify a mess as a complex, if we misidentify it as a complex tame problem, we'll attempt to solve it piecemeal. What will happen then is we'll evolve the mess and we'll make it worse. Now, there are two aspects to messes that we need to be aware of, and this will tie into how we understand architecture. One is interactive complexity. This is about what can go wrong in a system. So if I change one part, what's the impact later on? The other one is coupling, and this is not the same as the coupling that we talk about in software. This is the degree to which we cannot stop an impending disaster once it starts. This should hopefully illustrate this. I'm from Belfast, so it's easy. I'm allowed to use this example. So we have an iceberg, and we have a ship. Now, if we have a high degree of coupling, there's a good chance that the ship is not even going to see the iceberg. It's going to hit it, and it's going to sink. If we have less coupling, there's a good chance that you might actually just go slower, not hit it at all, or you might be able to see it and avoid it. So you might be able to back out of the disaster before it happens. So this is coupling. Okay, so we'll stop for a second, and we'll think about systems. So we have a system. This is this tangled mess of blobs. This is a system with a bug in it. Okay. Obviously, none of us will write systems that are a mess like this, so we'll refer to this as legacy code. So we have a legacy system, and what we'll do is we'll try and fix it. So we'll say, well, the best thing to do is we'll get, obviously it's a bug, so we don't want to spend too much money on it. We'll get somebody inexperienced who has the highest commit rate, because obviously the more code you commit, the better the developer you must be, and he'll fix it, and he'll produce this. Okay. So he's actually kind of, maybe, sort of, fixed it, but he's added a whole bunch of cruft. I was going to say something else there. Now contrast that with refactoring. Refactoring is when we do that. Refactoring is when we go in and we actually clean up the mess a little bit. We take stuff out and in the meantime fix the bug. Obviously, refactoring short term is more expensive, long term it's cheaper, right? So this is the situation we're in. Now there's a third and a final way we can characterize problems, and that is by wickedness, okay? So again, these are proper scientific terms. You have to trust me on that. So wicked problems are really problems where smart, informed people disagree. They're opinion-based, okay? So things like the war on drugs, the solution to that, the war on terror, what does that mean? And they're evolving over time, okay? So the point is, a lot of people, a lot of opinions, and people disagree. Smart people disagree. It's not that some people are right and some people are wrong. There's different opinions. So the thing to understand about wicked problems is that there's no definitive problem, okay? Now, if there's no definitive problem, then there's clearly no definitive solution, right? Because we don't know what the actual problem is. And so we can't solve it in a linear or waterfall process or any simple way. We can't take a simple approach to solve it. And there are no stopping rules, okay? So if there's no stopping rules, we're not done. We're never done. We're only done when we exhaust resources. And when we are done, we're actually not sure, did we do it well or not? We kind of know maybe that it's better or it's worse, but that's as good as we can do. And poor choices create more wicked problems. So if anybody's thinking here, order protection rule in regulation NMS or consolidated tape, then this would be a perfect example of thinking you've solved the problem, but actually you've just made it worse, a lot worse. Okay, so we'll whiteboard this. So if we plot the essentially the behavioral complexity against the dynamic systems complexity, we find that the mother of all problems is actually the wicked mess, right? So this one up here. Now it turns out that the wicked mess, or as we move in this dimension, we need to rely more and more on qualitative assessment, less and less on quantitative assessment. So while we think we can easily assess how we're doing, we can't do that. It also means that managerial approaches don't work so well. They work okay for tame problems. You can basically come up with processes and sort of define your way through to a solution. But with a wicked mess, no chance, right? You need to really take a more leadership type role. You need to show how to do something, try it out. If it's better, it's better. If it's not, it's not. So if we go back to our domain, which is finance, and say, well, let's consider healthy markets, we can see that markets involve people, they involve systems, and in fact, whenever this slide tricks on to the next one, okay, lots of people and lots of systems. So when we want to think about healthy markets, we're trying to say, okay, what are the things that we can use to define healthy markets? I mean, transparency, liquidity, volatility, and so on. And then how do we define these? What makes these things, what's good or bad about these things? Well, we can't really decide that, right? So what we can agree on, though, is we have a high degree of behavioral complexity and a high dynamic system complexity. So what we have when we look at our domain that we work in is we have a wicked mess, right? We've got lots of regulations, lots of opinions, lots of systems, lots of people. And obviously, regulations are promoted as the solution to this problem, but clearly they're not. And they're not because they basically can't change quickly enough. We'll come back to that in a second. So 2 key observations. The problem domain we are building for is a wicked mess, right? So this has an impact on what we're trying to do. And over time, software systems, again, because they're the product of people and their environment and influences, they themselves become a wicked mess. So in a way, we can actually start to use that as a definition of what we would consider architecture. In other words, we want to avoid the situation where wickedness and interactive complexity and coupling creep into our systems. If we can avoid that, then we can have more adaptive architectures, and we can test them. So back to my silhouette of the castle, which you can imagine. I've highlighted key points in this picture, which you can't see, but there are windows and other features of the castle under these. So imagine if we want to test this, right? So what we might do is we might start testing parts of it, and we might decide that we've got enough. We might need some more. There's actually a door down below in this last circle, so security breach, and we might try and test for these things. There'll be relationships between these. The point is, we can't test the system as a whole. It's costly, it's expensive. It's hard to do. We need to basically build an entire system to test it. So we have testing that's piecemeal, it's exploratory, and it's expensive. And we have no idea what the coverage is like, right? So it's not very useful. Okay, so the testing problem. First thing is component and unit testing does not reflect testing the architecture. This is the key observation. And testing the architecture itself is costly and slow and offers poor coverage. So we've talked about that. And we also have coupling. Again, you can't see this. I shall describe it to you. Basically, when we have complexity, coupling, and wickedness in the problem domain, there's a bleed into the solution domain, right? So the environment influences the architecture. We have this, because we're trying to change and adapt to this environment, we end up creating a solution which mimics it to some degree. Obviously, if it grows, then so does the solution. So there's coupling here, and we want to try and minimize that. So this is one of the things we have to do. Also, when we come to testing, we want to reason about a system like this, like building blocks, right? Where we can pump data in the top, we can measure things, and we can have deterministic results. But this is what we have. This is what we see, okay? Lots of code. So we want to reason about building blocks, but we can't. So with two challenges that we need to address. One is we want to decrease the coupling between the wicked mesh of the problem domain and the solution. And the other thing is we want to minimize the wickedness, interactive complexity, and the coupling in the solution. Now, it turns out that we can address the first one to some degree, and we can address that by looking at how we solve wicked problems. And there's a lot of research in this, and it's basically been shown that what you want to do, no surprises here, is you want a time box, and you want to iterate. And because we rely on qualitative progress assessment by expert stakeholders, we get these guys in the room, hopefully. We need good communication and transparency, and listening and trust, because remember, people disagree. So agile development techniques actually are what this picture is all about, right? So this is why agile development and agile testing and all these things that people talk about, what they do is they don't necessarily solve the solution or make the solution better, but they decouple you better from the problem domain. And that's the key thing. So it's not that agile makes it necessarily easier to develop, but it decouples you better and insulates you better from the problem domain that you're trying to build solutions for. So that's one challenge. The second challenge relies on an architecture. Now we call this an algorithmic architecture. This is an architecture that is based on well-defined building blocks. It has a clear mapping to code. It favors algorithmic optimization over task optimization, which basically means instead of optimizing elements or pieces within the architecture to improve performance or reliability or any other aspect of it, you optimize the architecture itself. So you can pull the architecture apart into building blocks and rearrange the building blocks, like writing an algorithm. And this allows an optimal solution and is adaptive to a changing environment. Now, when we get to the next slide, we can achieve this by doing a few things. Well, first of all, so I'm going to talk a little bit more, just briefly, about what an algorithmic architecture is. And that is that we can expose vocabulary. Now, the vocabulary that we expose must map to code, but it must be decomposable, right? It must be composable, so we must be able to take these blocks, combine them together, and build complex systems. The decomposability aspect allows us to reason about the architecture at different levels, okay? And it must be independently orderable. In other words, blocks within the architecture must be rearranged if there is no actual dependency between them. So this obviously implies less coupling. It must be compactable, because compactability allows us to speak, if you like, in full sentences. So if you imagine when you say a sentence, there are words in that sentence that are redundant to the information, but if you take them out, it becomes harder to understand. You need to think more about it. It's the same with architecture. We want to be able to have a sentence or a way to talk about an architecture in a domain natural vocabulary that we can obviously compress when some of these things are redundant. And it must be substitutable. I'm actually going to run over by about 2 or 3 minutes here, so we'll have some questions at the end, hopefully enough time. So substitutable, I hope we all understand why there's a duck here. Anybody not understand why there's a duck here? Okay, so the duck is for duck typing, right? This is the point. So if it swims like a duck, walks like a duck, and quacks like a duck, then it probably is a duck, right? And we want our architecture to be able to treat building blocks in that way. Now I'm going to skim through the next few slides. These next few slides are basically adding some meat on the bone. What does it mean to have building blocks? So for example, we might say that we have a vocabulary, but our building blocks are really just two things: buses to communicate through, and processors, stuff that does things. And that's just some example interfaces. We would avoid shared state. We'll favor message passing. We'll make synchronization points explicit. That's a very important thing. Why? Because synchronization points are not composable. So your architecture will have issues if you don't do this. And we'll support push and pull models. This is important for performance, particularly latency-sensitive applications. And lastly, well, almost lastly, we'll have separate data and command paths and static polymorphism for adaptability. Now, if we have all this, we can return back whenever this slide moves forward. Okay. Sorry. Okay, so simple example. We have a vocabulary and architecture. We can compress that. Okay, we can compact it, remove the redundant words, and then we can use our compilation phase or our runtime phase to generate our optimal solution. So what we might have then, for example, is we might have two different systems, the same building blocks, the same vocabulary, latency agnostic, scaling agnostic, across multiple servers on a single server. Doesn't really matter, but we were able to reason about this and we can rearrange these. So these are our building blocks, right? So this is our algorithmic architecture. So this addresses basically the last point. So if we return to the problem we're trying to solve, we want to test the architecture. This is our architecture. The point is you don't build castles, right? This is the thing. What you want to do, and hopefully you'll be able to see this, is you want to build systems like this. You want to build systems based on these simple building blocks. If you do that, you can test that. Well, you can't because they're quite big, but what you can do is you can separate them down and you can test them individually. And so if we test these individually, or each of the building blocks individually, so our component testing scales to our actual architecture testing, then we can actually infer and test the full architecture, which means we have composable and transitive tests. Now that's very important because that allows us to build and scale complex systems and have basically 100% coverage. And we also, if you notice these green things here, we can substitute in what we want. So we can actually replace, we can actually test an entire architectural stack by putting in placeholder elements, for example. And that is me finished. The conclusions are that problem one, we solve that with agile development. It decreases the environmental impact on the architecture. And if we adopt an algorithmic architecture, we can also allow effective composable testing, which will allow us to actually directly test the architecture or piecemeal test the architecture. And I'm finished. Thank you for listening.